Hello, my name is Ali and I'm a first-year PhD student at the University of Illinois Urbana-Champaign. In this video, I will present our recent work, Perfect is the Enemy of Test Oracle, which has been published at FSE 2022. I have completed this research project during my undergrad, along with other students as part of the University of Illinois Urbana-Champaign Software Engineering Summer Internship. And now, let's get started with the presentation. In the beginning, we should understand what is a test oracle. Generally speaking, test oracle is the problem of identifying whether a given test can reveal a bug in the code under test or not. If a test passes, it either means that the method under test is correct or test cannot reveal the bug. If a test fails, it means test reveals a bug. In this part, we will look at some of the existing work which tries to automate test oracle construction. The existing traditional and machine learning-based techniques rely on existing or derived formal specifications, assertions, program invariants, or metamorphic relations for identifying the correct behavior. The commonality between these techniques is that they try to determine the exact program behavior given the inputs and outputs. However, determining the exact behavior is an undecidable problem. Focusing on knowing or predicting the exact correct or incorrect behavior makes the oracle problem computationally unpredictable. But the problem is even worse, and I will explain why with an example. In the beginning, let's focus at this implementation here, which is a correct version of the mathematical function absolute value x times x plus 2 times x minus 2. And let's also look at a buggy implementation of the same function, which is only misplacing the absolute value at the end of the statement. The graph shown on the slide describes the behavior of the program. We can plot this graph for this example because the unit test is very simple, but as the complexity of the program increases, for instance, if we have user-defined objects and arrays as inputs, determining such graphs become infeasible. Now let's also look at some unit tests. Unit test 1 is based on program invariance, which is trying to look at the existing execution traces and determine the behavior of the program. Since it's only considering the buggy example, it tries to verify if the output is bigger than or equal to 0 for x equals 0.5. Similarly, unit test 2 is based on metamorphic relations, and it tries to find out whether f of minus x equals f of x. As you can see from the graph, the behavior of the buggy program and the correct program do not match in the interval x bigger than minus 2 and x smaller than 2. In a nutshell, all existing work need to know the correct or incorrect output for given input. Next, we will discuss how our proposed technique can overcome all of these challenges. In this work, we propose SEER, which is a deep learning enabled technique for automatic test oracle construction. Our key idea is that we can still create an accurate test oracle without knowing the exact expected behavior or explicit relationship between inputs and outputs, but with only knowing how inputs and outputs are differently correlated under the correct and buggy behavior. As you can see from this figure, our goal is to learn the correlation between the inputs and outputs by minimizing the distance between the test and correct implementation and maximizing it between the test and buggy implementation in the embedding space. We can achieve this through contrastive learning of a test that passes on the correct code and fails on the buggy code. In this part, we will discuss more about the model interpretation of SEER. While SEER attempts to solve an ever-challenging Oracle problem, we wanted to see if we can leverage its learning capabilities to enhance bug localization. The key idea here is that if we interpret the learned model and understand how it predicts if a test fails on a given method under test, this can help to root cause the bug. For instance, let's consider the buggy implementation we have discussed earlier. As you can see from these attention weights, if the model looks at the open and close parentheses to make a prediction, it would be enormously helpful for the developer to root cause the bug. In short, we can say that SEER bridges the gap between testing and debugging. Next, we will discuss more about the attention analysis algorithm of SEER. Since SEER has a transformer encoder in it, we have used the self-attention weights in order to determine which tokens are most attended by SEER when making a decision. The inputs to our algorithm are the MUT tokens, MUT statements, self-attention weights, and attention threshold K. In short, attention threshold K means we are interested in top K most attended statements by SEER. As you can see from the figure, first we iterate over each row of the matrix and get the column of the most attended token and call it local attended token. Then we iterate over the column and store all of the local token values. At the end, we look at every stored statement and check if its ranking is higher than K. If it is higher, we store and later use it for our analysis. In this part, we will look at some of the research questions we have explored in this work. Our research question 1 is about effectiveness of SEER in predicting test labels. Our second research question is about generalization of SEER to unseen projects. The third RQ is about interpretation analysis of SEER. In this research question, we focus on analyzing the reasons behind SEER's decisions. In the last research question, we investigate the performance of SEER. More specifically, we want to know how long does it take for SEER to predict a test verdict. Due to the time constraints, I will only talk about our RQ1 and RQ3 in this presentation. Please refer to the paper for a discussion on other RQs. As for the experimental setup, we've built SEER's dataset on top of the Fix4J. The table shows some statistics of the dataset. Our dataset consists of real bug and syntactic bugs. For the real bugs, we've exported realistic bugs from the Fix4J. And for syntactic bugs, we've generated higher order mutants using major mutation testing framework. On the other hand, our tests are a mix of developer written tests, which are coming from the Fix4J, and Randoop tests, which have been automatically generated by Randoop test generation tool. Now coming back to research question 1, in this slide you can see the evaluation of SEER on test set. In order to make a fair evaluation, we decided to keep the same project distribution in training, validation, and test set. The total size of test set is 5,080 instances, which is roughly 5% of the whole dataset. As you can see from the table, SEER achieves an overall 93% accuracy, 86% precision, 94% recall, and 90% F1 score. For a detailed explanation and discussion of results, please refer to our paper. As part of an ablation study, we were interested in determining whether SEER prefers shorter or longer sequences. Our results showed that the longer the MUTs and tests, the better the performance of SEER. Next, we will discuss the result of our third research question, can SEER find buggy statements? This research question is mainly about the interpretation of SEER. As you can see from this graph, the x-axis shows the attention threshold. More specifically, an attention threshold of K means the top K most attended statements by SEER. The y-axis is the percentage of discovered buggy statements, which is the total number of attended buggy statements divided by total number of buggy statements times 100. The figure shows that even with a small attention threshold of roughly 5%, SEER can attend more than 50% of buggy statements. This indicates that SEER is mostly focusing on buggy statements when making a decision. Moreover, you can also see that as we increase the threshold, the percentage of the attended buggy statements also increase. In a nutshell, we can conclude that SEER is effective on enhancing bug localization. As part of another ablation study, we also wanted to see at which specific tokens of code SEER focuses to predict a label, and if those tokens are relevant to bugs. In this section, we will discuss the results of our ablation study. Can SEER find buggy tokens? We have used a realistic example from our dataset in order to show the results of this ablation study. More specifically, this specific instance is a true negative in our results. That is, the test which tests this MUT is a failing test, and SEER correctly predicts it as a failing test. The goal of this analysis is to see which tokens receive the most attention from SEER when making the decision. The figure on the right corresponds to the self-attention weight of the transformer encoder block. We use a heat map to represent the attention weights in order to show the attention intensities. The token true, which is pointed out on the slide, corresponds to the change token between the buggy version of the program and the fixed version of the same program. As you can see from the attention weights, SEER indeed attended to the change token between two code versions when making a decision. Similar to the previous example, I'm going to explain another true negative instance from the dataset. As you can see, there are multiple bug fixes in this example, and each bug fix are in different line. As you can see from the attention weights, SEER indeed attended the change token along other important tokens when making its decision. This indicates that SEER is also capable of understanding complex bugs. In the last slide, I will list some of the conclusions from our work. In this study, we propose SEER, which is a deep learning enabled technique for automated test oracle construction. SEER learns how inputs and outputs are definitely correlated under the correct and bugging behavior rather than understanding the exact program behavior. Moreover, we also go beyond a closed box solution and make SEER an open box solution. In short, we can say that SEER's model is interpretable and can enhance bug localization. Finally, we show that SEER is highly accurate and generalizable to unseen projects. In the end, I want to mention that we have open sourced all datasets and artifacts of SEER on GitHub and Zenodo. Our artifacts have received the artifacts available and artifacts evaluated functional from ACM. Thank you.